Welcome to the second lecture of Electric Flux and Field Part 2, and in this we are going to discuss more about electric flux, something about Gauss theorem, the applications of Gauss theorem, and before we start off with anything I would like to review the topics. But this is a very sincere suggestion. If you haven't seen the video on electric flux part 1, please go and see it. I'll post a link for the same. Now, moving on, as I had discussed before, that if there is a charge inside a closed surface, or let's say just a charge and the surface is imaginary, the charge emits a fixed amount of flux. And do you remember what was that fixed amount of flux equal to? That fixed amount of flux was phi equals to q by epsilon naught, and that was only dependent upon the charge. And as the flux spread through the surrounding space, let's say as the flux spread in the surrounding space, it's a very bad sphere to draw, but okay, as the flux spread in the surrounding space, the intensity of flux decreases. Intensity of flux decreases. And what do we call as intensity of flux? We call intensity of flux as field. For a point charge, the field is q by 4 pi epsilon naught r squared. If you try to divide it into two parts, it is going to be q by epsilon naught, that is the flux, and 4 pi r square, that is the area. Now there is something interesting about positive and negative charges here that I would like to mention. The most important thing about positive charges is that a positive charge is a type of charge that spreads flux around space. This here is a very good representation of what we can call as flux due to positive charge. A negative charge, on the other hand, I have a negative charge minus q. It absorbs flux. You might have this might have come up across the discussion that positive and negatives are simply conventions. Positive and negatives are simply conventions, and the signs have got nothing to do with the charges whatsoever. They are simply names, as your name is, or as my name is, or as anybody's name is. Positive and negatives are simply names. But what is the main and major important difference between a positive and negative charge? So a positive charge emits flux, and a negative charge absorbs flux. And if it is a point charge, how much flux does it absorb? It absorbs the same amount of flux, and that same amount of flux is q by epsilon naught. So intensities work both ways, and that is why field for a negative charge, the field for a negative charge is going into the charge because the flux is being actually absorbed by the negative charge. There were some other points of discussion that I was talking about, and those points are very important. They need to be discussed. So let's say I have a charge here. That charge is q and it emits field. This charge is emitting field here. We had discussed before that flux is a scalar quantity, whereas field, we all know that, is a vector. Now, if we want to find out flux of this charge, what do? We have to find out the flux due to this charge. We already know it's q by epsilon naught, but okay, we want to go the other way around and we want to find out the flux due to this charge. What do? The way to do it is very simple, that we take a point P on the surface, and let's say it has a distance r, and we take a very small area around P. That area is what we call as ds. Let me call this area as ds, and we take an area vector ds vector, and the field, as you can see, is this direction. And the way to find out flux is phi. The way to find out flux is phi is equals to E dot ds, and we integrate it for the entire surface. Now in this case, in the case of a sphere, you will notice, and it's very important here to understand, that you take any area that you take, whatever area that you take, is always parallel to the field direction. So the dot product, if all areas are parallel to the field direction, in all cases the angle is theta equals to 0 degrees, and the dot product becomes equals to E into ds, and cos 0, that becomes equals to 1. And what is the value of E? And then we'll integrate it, obviously. What is the value of E here? The value of E here is q upon 4 pi epsilon naught r squared. And what is the total area? Because we are integrating, the total area was 4 pi r squared, and 4 pi r squared and 4 pi r squared gets cancelled out, and the flux becomes equals to q by epsilon naught. Now if we have a strange area like this, let's say I have a strange area like this, and I want to find out the flux due to this, let's say, okay, so I want to find out the flux due to this charge. Now this charge is emitting field in all directions, and there is a surface. If you're not getting what surface we are talking about, let me draw a three-dimensional view of the surface. Let's say it's like this, so it would be something like this, and this is the charge here, and okay, so this is the charge here, and the charge is emitting field like this, okay, and we take a small area, and we take a small area, and we take a small area on this surface, and this area vector will have a different direction. Now the three-dimensional thing is getting really difficult right now, so we switch back to the two-dimensional thing right now, right? So here we have a charge q, and we have a small area like this, and the area vector is, as you know, always perpendicular to the area, ds vector. And then you have this is the field, obviously, and then you have some angle here, theta angle, and likewise you can have all these things here. This is another ds dash, let's say, and this is another one, let's say this is ds double dash, okay, and you will have to find out E dot ds for this entire surface, or let's say for this entire surface at all points on the surface, right? And then you will integrate it, and then you will get the value of flux, whatever it is. Now you must know that in an open surface like this is an open surface. Can you see? Open surface. And we are not going into the mathematics of it. We'll come to mathematics. The mathematics involves integration and a lot of stuff. We are not going to do it. We are going to treat it very simply right now. Integration will come. Please have patience. Now this is an open surface, right? So if we have an open surface, we must understand one thing that is very important. And what is that important thing here? Let me consider this diagram here, right? So the one thing that is very important is any charge. Let's say this is our charge q. Any charge emits a total flux of q by epsilon naught. Now when I say total means that it is emitting in all directions. Right? Now some of this flux, as you can see, some of this flux is passing through the area, And there is also some of this flux that is not passing through this area. Can you see that? So this flux here is not passing through the area, whereas this flux here is passing through the area, and the total flux is q by epsilon naught. So we can say if this is our area, coming back to the two-dimensional diagram, if this is our area, the flux through this area will always be less than q by epsilon naught. Why less than q by epsilon naught? Because the total flux of a point charge is q by epsilon naught, right? Now this is a very simple question. This is what you see here. Here is an inclined plane. And this is a surface. It has an area. Let's say it has an area A. And a field is passing horizontally. There is an horizontal field. The question is very simple. The question is simple. What is the flux of E through area A? That is the question. And we have to solve this question. The best ways to solve a question is always to convert it into two-dimensional formats. So I'll convert my question into a two-dimensional format. This is again my inclined plane. And how am I looking at the inclined plane? I'm looking at the inclined plane at this viewing angle. I'm looking at it at this viewing angle. So this inclined plane at this viewing angle looks like this, right? And the field is obviously straight. It's passing through this like this, and the field is passing. I can draw, right? The field is passing. This is your field, and this is the area. Now the question is, and this angle is obviously theta. Now the question is, what is the flux? Now, as you can see, that the area that we are talking about is like this, and the field we are talking about is like this. And what is the area vector that we can take? We can take an area vector like this, or we could also take an area vector like this. It's entirely your independence how the area vector you have taken. But sometimes it becomes very cumbersome to deal with negative quantities, and I'll tell you why. If you take this particular area vector, and let's say that this angle is theta, this angle is theta, so this angle is going to be obviously theta again, and this is going to be 90 minus theta. So if you take this as your area vector, the flux would be read as E into A into cos 90 minus theta. That becomes equals to sin theta. And if you take your area vector as this one, the angle between them would be, you can see this angle is, this angle is 90 degrees. So the angle between them would be 90 plus theta, and the flux would be written as phi equals to E into A into cos of 90 plus theta. That would be minus sine theta, and the flux becomes negative. In open areas, it does not matter what kind of flux you take positive flux or negative flux, but generally it is a convention to prefer positives over negatives. I mean, that's a standard convention in mathematics. If you take any imaginary number x, you assume first hand that it is a positive number. It may be or may not be positive, but you assume first hand that it is a positive number. So that is the convention that we are following here. Now the most important thing here is something that we haven't noticed yet. And what is that? That is that when we are talking about this area here, let me show the arrow, this area here, and let me draw the area again here. When we are talking about this area and we are saying a sine theta, so a sine theta is basically this area here, a sine theta. And as you might have noticed, the field is in this direction, and the area vector of a sine theta would also be in this direction, because what do we know about area vectors? Area vectors are always perpendicular to the surface. So this is your surface, this is your surface here, and a sine theta area vector is going to be perpendicular to the surface. So we come back to the initial definition. Whenever we find flux from fields, we always take an area vector in the direction of field. Now this is yet another question, and it is slightly more difficult. You see, a charge q is placed at the axis of a disk or a ring. So this might be a disk, this might be a ring, and why it doesn't make a difference, I'll tell you. And what is the flux of the charge through the disk or the ring? So this charge has a flux that is going out in all directions. So the charge must have a flux. The charge must have a flux. The total flux is all we know. We always know that. What is the total flux? The total flux is, there is no denying that, the total flux is q by epsilon naught. So that is not something that we care about. What we are interested in is this, that what is the flux of the charge q through this disk or ring, whatever you like to call it. So let's consider the field of the charge q at a certain point on the disk or the ring, as you like to call it, would be something like this. Now you can see that this distance is x, and we don't know what this distance is. We don't exactly know what this distance is, so we will call this as unknown distance r. At this distance, the field is going to be something like this. What is the field at this point P? Field at point P is going to be k q upon r squared. R squared, that is distance squared. And what is the distance from the charge q to that point P? The distance from the charge q to the point P is x squared plus r squared. That is your field. Now you will notice that k is obviously constant, q is again constant, x is constant because you can never change the position of the charge as far as the question is concerned. But what we are noticing here is this, that is, if we change the r, or we try to find out the field at a different point, let's say I want to find out field at this point. When I want to find out the field at this point, I would notice that there will be a different distance from the center. This distance in blue, that is going to be r dash, am I right? So if the distance changes, the value of field also changes, because the value of field is dependent upon r. So there is a problem here. If you take a common r, let's say you take this r here. If you take a common r, the field is going to have same value at all places, same value. But if you take a different r dash, let's say you take this r dash here, the field is going to take different values. So I'll say it again. So if we take a common r, let's say on all these yellow points, the field will have same values. Not same directions, but yes, same values. If we take all the blue points with distance r dash, the field will again have same values but different from those of yellow points. So what do we do in this case? Okay, so I have drawn the diagram again. So this is my charge Q. It has a field like this. At this point the value of field is going to be this, and we want to find out the flux, not on the entire disk or the ring area, but we want to find out the flux on this thin ring type area here, on this thin ring type area here. So if you have this ring type area, there will be an area vector that will be perpendicular to the area. So the area vector will be something like this, ds. Now how do you take areas in thin rings? If you might remember the old things that you have worked upon, in order to take areas in rings, what do you do is you take a radius, that is r, and you take a width, that is dr, and then you open up the ring to form a rectangle, a very thin rectangle, and then you simply find out the area of the rectangle. So what is the area of the rectangle? The area of the rectangle is 2 pi r, that is the length, and dr, that is the width, and the area of the rectangle, that is ds, it becomes 2 pi r dr. And we have the value of ds now, we have the value of E now, and we can now calculate the value of flux. So I'll find some space here because you need to understand it from the diagram. The flux is going to be E ds cos theta. Let me write the formula first. E ds cos theta, where E is going to be kq upon x square plus r square. Ds is going to be 2 pi r dr, and cos theta, as you might notice here, cos theta by corresponding angles theorem, the cos theta is going to be this is r. You can see this this is okay. Okay, this is r, this is x. So what is cos theta going to be in a right angle triangle? The cos theta is going to be the base, that is x, by the hypotenuse, that is root under x squared plus r squared. And this is the flux that we have found only for the yellow area. You can see the yellow area. This is your yellow area, and this is the flux. This flux is only for the yellow area. Now we know that flux is scalar, obviously, and we don't need any kind of directions in flux. Whatever flux we have, it's a scalar quantity. So all we have to do is add up the flux for all such areas. As you can see, the blue area here would be a different area for r dash, and then there could be another area, let's say an area like this, green area, something. You can have an area like this, and with those areas you can cover the entire area of the ring or the disk. So you can have multiple areas and you need flux through each of those areas. So let's write down what the flux was. The flux was kq upon x squared plus r squared into area, that was 2 pi r dr, and there was cos theta, that was x upon root under x squared plus r squared. In order to integrate this flux, I'll just draw a rough diagram here. Okay, not working very well. Right. In order to integrate this flux, please do remember at this point of time that this was x, this was r, and we had this angle that was theta. So we had something that was r is equals to x tan theta, and dr would become equals to, what is dr? Let me show you. This is the small width is obviously dr. So dr would become equals to x sec squared theta d theta, and then we are going to substitute the entire thing in the flux. So that was kq upon x squared sec square theta into 2 pi x tan theta into x sec squared theta into x upon x sec theta. So this is what we are getting, and you can simplify all these things. So you can see that there are three x's in the numerator, x, and x, and we have 3x in the denominator, that is x squared and x. So all the x's is getting out of the scene. One sec squared theta and one sec squared theta is getting out of the scene. Then we are only left with tan theta by sec theta, and that becomes equals to sin theta. So your entire value of flux is getting reduced into kq 2 pi. What else? Let's see here, sin theta d theta. Are we missing anything? Nope. So let me write it again. Flux is going to be kq 2 pi sin theta d theta, and then we integrate it. And how do we integrate it? So let me draw the diagram again. This was your ring here, and this was your ring here, and this was your charge, and this was the angle theta that you took. So your angle theta is varying from what to what. If you take the smallest possible ring, your theta is 0. For the smallest possible ring, theta is 0. And if you take the largest possible ring, that is here, your angle is, let's say, going to be alpha. So what are the values of theta in which we are integrating? We are integrating from 0 to alpha. The smallest angle is 0 and the largest angle is alpha. So we are simply going to write 0 to alpha. And that becomes equals to, if you can simply substitute the value of k with 1 by 4 pi epsilon naught, that becomes equals to q upon 2 epsilon naught into 1 minus cos alpha. And this is the flux of the charge through the ring, this charge q through this ring area. Now why I said that there is no difference between a ring area and a disk area? An area is an area. If you take a ring, you take a disk, it does not matter. An area is an area because the flux is passing through all points on the area. There may be a material, there may not be a material, it does not matter for us. But an area is an area, so either we could take a ring or we could take a disk, it remains the same. The flux of this charge remains the same, and the flux of this charge is q by 2 epsilon naught. Now what is the interesting thing to notice here? The interesting thing to notice here is that the total flux of any charge is q by epsilon naught. We have discussed this before, I am saying it again. The total flux of any charge is q by epsilon naught. And as you can see in the diagram, there are many field lines that are never going to cross this area. There is a large number of field lines, I would say there is a majority of field lines that are never going to cross this area. There is only a select group of lines that are going to pass this ring area. And those select group of lines form what we call as flux. And the flux here is obviously less than flux through the ring or disk, whatever you like to call it, is less than the total flux, because the total flux is something that gets distributed into entire space. This is very important to notice here, the layman definition of flux, and it sounds funny, but it is going to help you understand a flux sometimes. What is layman definition of flux? The first thing is, you must understand that you can never see or feel flux. That is impossible. You can never do that. That's not possible. right? You can never see or feel flux. You can only experience force. And since you can experience force, you can divide the force by charge, test charge that is you like to call it, and becomes equals to field. So you can experience force, you can derive your field from it, but flux is something that you can never see or feel. I mean, flux means nothing to you. I mean, what is Q by epsilon naught? Is it power of a bulb, or it's just anything? We don't know. We don't know what flux is. We know there is something called as flux, but we exactly can't understand qualitatively what flux is. We define flux as something very interesting. We define flux as the number of field lines, passing through a surface. It's a very stupid definition, number of field lines passing through a surface, and I'll tell you why it is a stupid definition. I have a charge Q, and we know that the total flux of this charge Q is Q by epsilon naught. So the total flux is Q by epsilon naught, and you can draw 4 lines coming out of it, you can draw 6 lines coming out of it, or 7 or 8. How many lines you want, you can draw coming out of it. But this physical quantity Q by epsilon naught can never be a number, can never be an integer, not number. It is, we will always have a number, but it can never be an integer or a positive integer. Why can it never be a positive integer? Because epsilon naught, you know the value of epsilon naught, right? The epsilon naught is 8.85 into 10 ka power minus 12 in SI units. Now, I'm not going to discuss units now, but we know that this is the flux, and you can see that I don't know if you know about this. 8.85 is not an integer. It is not even a rational number, because 8.85 is just first 3 values of this constant epsilon naught. All universal constants as we know them are all irrational numbers. They are all non-terminating, non-repeating decimals. They can never be put in a p by q form, and hence you can never have this physical quantity Q by epsilon naught as an integer. So if this cannot be an integer, saying that flux is number of field lines, please notice again, number of field lines is a stupid thing to say, but it really works on a lot of levels. And how does it work? We shall see that. So we have taken a charge here. This charge is Q, and I can draw any number of lines here, any number of lines. Let's say I start with how many lines should I start with? Okay, 4 lines are there, so 5, 6, 7 and 8. I start with 8 lines. So I'm saying that there are 8 lines here. Now what is the correlation or the comparison between flux and number of lines? What is the connection here? We know that flux is constant, Q by epsilon naught. And we also know that if you take a specific number of lines, for example in this you have taken 8 lines, the number of lines will also be constant. So as those number of lines start to get distributed in space, the number per unit area, or you can call intensity, that will become 8 upon 4 pi r squared. That will be intensity of lines, and here it will be intensity of flux Q upon epsilon naught upon 4 pi r squared. So this is a very good comparison to begin with, that since flux is constant, and if we take a fixed amount of lines coming out from a charge, they would also remain constant. Hence we can compare. We cannot say they are equal to, we cannot say they are the same thing, but we can compare that the flux is number of lines coming out of a charge, or number of field lines to be exact. Flux is number of field lines coming out of a charge. Now here you must understand that if it is a negative charge, there will be number of field lines going into the charge, so you can change it automatically. Please don't get confused. Okay, so I had this diagram ready made. You can see there is a charge here. There's a charge here, and the charge is on a there's a line here, and there are two discs on that line placed very symmetrically. And what does symmetrically mean at this point, I would like to tell you. Let's say this distance is r, and this distance is r dash, and let's say this distance is d, and the entire distance, the big distance here, this distance here is d dash, for suppose. So symmetry simply means, the symmetry would mean that r upon d that is similar triangles method, that is r dash upon d dash. Now back to the situation here. Now I have a charge q here. I have a charge q, and this charge q emits field lines. So I have these two blue field lines, that are basically passing, almost touching the edges of the disk. And then we have other field lines also that are passing inside from within the disks. And let's say you draw a certain number of lines. Let's say you draw, how many have we drawn yet? How many blue lines are there? So we have 4 blue lines. Let's draw a few more. We have, let's say 5, and let's say we have 6 now, and let's say we have one more, 7. We have 7 field lines here. Now all these 7 field lines, if these two disks, if the two disks are placed symmetrically, again, what does symmetrically mean? Symmetrically mean this similar triangles thing. If these two disks are placed symmetrically, the number of field lines that cross the disk, that is that is the smaller disk, will be equal to the number of field lines that cross the larger disk. There are other field lines also. I'm not saying there aren't any more field lines. There could be some field lines like this. But if a field line doesn't cross the smaller disk, it also doesn't cross the larger disk. So you have a lot of field lines going in other directions. I'm not denying that. But if these two disks are placed symmetrically, again, symmetrically means they are following the similarity, the laws of similarity. We can say that the number of field lines, and what are the number of field lines? Let's start counting. 1, 2, 3, 4, 5, 6 and 7. So 7 field lines, and those field lines are crossing disk, the smaller disk as well as the larger disk. So we can state a very important thing here, that flux through, let's call this as disk 1 and let's call this as disk 2. So flux through disk 1, that is phi 1, is flux through disk 2, that is phi 2. Because any number of lines that would pass from disk 1 would also pass from disk 2. And that is the reason why we compare. We do not say that they are the same. We compare electric flux with the number of field lines, because number is something that is going to be constant. Now this is an interesting question here, and we have a charge q inside a cylinder, exactly at the center of the cylinder. By all considerations of the symmetry, the charge q is at the center of the cylinder, and we have some distances here. Let's say the radius of the cylinder is r and the height of the cylinder is 2r. Now the question that is being asked to you is very simple. What is the flux of charge q through the curved surface? Through the curved surface. What is the flux of the charge q through the curved surface? This is your curved surface here. This is, you can see very easily, the curved surface. Now we are going to use a particular formula that we have derived in this explanation itself. If there was a ring or a disk, I think you remember, there was a charge q, and the maximum angle was alpha. The flux of the charge q through this ring was q by 2 epsilon naught into 1 minus cos alpha. If you don't remember it, please go back into the lecture and watch it again. So this was the flux of charge q through this disk or ring, whatever you like to call it. Now this charge q has all kinds of field lines, Some field lines are coming out of the circular surfaces, some field lines are coming out of the cylindrical curved surfaces, some field lines are coming out of the curved surfaces, the circular surfaces on the top. It has all kinds of field lines. But we want only the flux through the curved surface. Now, how do we find the flux through the curved surface? The total flux is going to be phi equals to q by epsilon naught. That is not changing, that is forever constant. Total flux is going to be q by epsilon naught. This is our charge q, right? Now there is some flux through the circular surfaces. There are two circular surfaces, here, and then there is a curved surface, that is here. Now, what is the flux through the circular surface? Because we know the formula. Now you can see that from the charge here, the perpendicular distance to the center of the circle is r. Why it is r? Because the height is 2r, so half of it is going to be obviously r. So this distance is r, and the radius of that disk is also r. So if both are r, the angle alpha is how much? 45 degrees, obviously. So what is the flux through the disk or the circular surface? The flux through circular surface is phi c equals to q by 2 epsilon naught into 1 minus cos 45, that is 1 by root 2, obviously. And the flux, since there are two circular surfaces, the flux through the second circular surface is also going to be the same. Flux through second circular surface is also going to be phi c2, let me call this one phi c1, q by 2 epsilon naught into 1 minus 1 by root 2, right? So flux, total flux through circular surfaces is going to be the addition of these two, the sum of these two fluxes. So it is going to be obviously q by epsilon naught into 1 minus 1 by root 2, correct? Now back to the diagram. If you might notice, if you have found the flux through this circular surface and you have found the flux through this circular surface and you already know what the total flux is, I guess you would know what the flux through the curved surface is going to be. Alright, let's leave it at that. So the flux through curved surface is going to be the total flux phi naught minus flux through circular surface. So q by epsilon naught minus q by epsilon naught into 1 minus 1 by root 2, and that will be equals to q upon root 2 epsilon naught.